fluorescent paint, and black lighting.
The term blacklight first appeared in print in 1896, used by the French sociologist Gustave Le Bon for his newly discovered invisible light. Le Bon, a black light from an oil lamp flame passed through a steel-plated box and completely exposed a photographic plate inside. In Philosophical Magazine, Le Bon wrote that opacity only exists for human eyes, and not for light, and that if the human eye were somewhat differently constructed, we could see through walls. As it turns out, he was wrong. In 1903, Robert Williams Wood, a physics professor at Johns Hopkins University in Baltimore, developed a glass filter that blocks visible light, but allows ultraviolet light to pass through. Wood used his filter to take the first ultraviolet photographs. In the 1930s, William H. Byler worked at the General Electric Company laboratories in Schenectady, New York, where his research included discovering how electricity could be used to study and cure disease. In 1935, Byler developed the ultraviolet black light bulb. In the 1940s, Byler suggested using black light to illuminate airplane cockpit instruments. A black light will make anything containing phosphorus seem to glow in the dark. A phosphor is any substance that absorbs energy and re-emits it as visible light. The ultraviolet light emitted by a black light finds these phosphors and turns them into visible light. Most of the light a black light emits is in the ultraviolet range of the spectrum, which makes it invisible to the human eye.
Fluorescence is the result of a three-stage process that occurs in certain molecules, generally polyaromatic hydrocarbons or heterocycles, called fluorophores or fluorescent dyes. During the first step, called excitation, a photon is supplied by an external source, such as an incandescent lamp. This photon is absorbed by the fluorophore, creating an excited electron state. The excited state only exists for a certain amount of time, usually 1 to the negative 10 times 10 to the negative 9 seconds. During this time, the fluorophore undergoes conformational changes and is also subject to many possible interactions with the molecular environment. These processes have two consequences. First, this partially dissipates the energy of the excited state, which creates a relaxed excited state, which is where the fluorescence emission originates. Secondly, not all the molecules initially excited by absorption, stage 1, returns to the ground state by fluorescence emission. A photon of energy is emitted, returning to the fluorophore to its ground state, 0. Due to the energy dissipation during the excited state lifetime, the energy of this photon is lower, and therefore of longer wavelength. The difference in energy or wavelength is called the Stokes shift. The Stokes shift is necessary for fluorescence techniques because it allows emission of photons to be detected against a low background. Absorption spectrophotometry requires measurement of transmitted light relative to high occurring light levels at the same wavelength.
Blacklights have a wide range of uses. The most common use for a blacklight is for lighting effects. Stage products sometimes utilize their unique effects, and many people like to have them in their home just for fun. Some corporations use a clear ink that can only be seen under a blacklight on various tickets and banknotes. This ink is clear, and under a blacklight it fluoresces. Also, this ink is used on some currencies in order to make it easier to detect counterfeit. Some of these currencies are the US dollar, the British pound, and the euro. This ink is also used at some amusement parks and nightclubs in order to keep track of the people who have paid for entry. Hotels use blacklights to make sure the rooms are being cleaned properly. Traces of urine and other fluids that cannot normally be seen show up under a blacklight. Special ink can be used to mark merchandise to protect a business from theft and fraud. Blacklights also help make your nightclub or laser tag experience a little bit more fun. A particle of light is called a photon. It has no mass, just energy. When this packet of energy comes into contact with an electron in the outer regions of an atom, the electron absorbs the energy and jumps to a higher energy state. The electron cannot stay in that state for long. It releases that energy as a photon of light, but the new photon has a slightly lower energy level and thus a longer wavelength. Every substance interacts with light in this way. People typically do not see it because the light given off is of a wavelength that cannot be seen, or there is too much light around to see the emission of the photon. This is the glow effect associated with the black light. The brightness of the glow depends on the amount of ultraviolet light applied and the sensitivity of the material. In this diagram, an externally supplied high-energy photon, in this case from a UV lamp, is absorbed by the electron and creates a high-energy excited state for the electron. The electron exists in this state, which is further away from the nucleus, for a very short time. During this short time, the energy dissipates, and after this, a photon is released, and the electron returns to ground state. This photon has a lower energy than the one supplied, and because of that, a longer wavelength. The photon has less energy because during the time that the electron existed in the excited state, its energy dissipated. Because the photon has a longer wavelength, this causes the atom to fluoresce, and thus creating the glow that you see. This diagram also shows the fluorescent process. The blue arrow represents the high energy photon that is absorbed, and it creates an excited state for the electron. The red squiggly line shows the dissipation of the energy in the excited state for the short duration in which the state exists. The green arrow pointing down shows the electron going back to ground state, and the squiggly line branching out from it is the lower energy photon which is released. This also causes the atom to fluoresce, which is the glowing.
These are the main points of fluorescence and black lighting. Black light, ultraviolet or infrared radiation, invisible to the eye. Fluorescence, visible or invisible radiation emitted by certain substances as a result of ultraviolet light. Quantum mechanics, as electrons jump to a lower energy level, they emit a photon that under a black light is fluorescent.